There we go. All right. So we're going to talk about the LabVIEW security primer. We want to be able to speak the language of security just like a lot of the other text languages do, but we need to do that from LabVIEW, which has some unique requirements and challenges. So first, to introduce myself, my name is Hunter Smith. I'm the security program manager at JKI. I actually started my career working for NI doing K-12 robotics, Lego Mindstorms and FIRST Robotics. I then spent nearly 7 years at SpaceX working on rocket engine test systems and ground systems for the Starship. I'll let you guess who the more challenging customer is, elementary school students or rocket scientists. Sometimes it's a toss-up. For the last 3 years, I've been at JKI, and that's given me a chance to work on a lot of different projects in a lot of different fields. And I want to tell you about one of them to start us off here. Right after I started at JKI, we had just won a contract to overhaul the data system for the NASA Ames ArcJet complex. This is a thermophysics facility where they have basically a hot wind tunnel that can blast plasma at a test article like a piece of heat shield tile. And we created our JKI Stargoat app as the main data system for that. But because it was done for NASA, we had to comply with the full 7150.2D software development process, which included numerous security requirements. And what that boiled down to is trust. Is not only did they want to have the code that met the requirements, but they needed to trust that it was going to do what it said it was going to do, that it was going to be stable, that it was going to be performant, and that it was going to be secure. I know a lot of you in the audience might have written code for NASA or for Department of Defense or other agencies, but there's a lot of reasons that you need this level of trust in your code. You may be working on aerospace projects that deal with lots of energy or transport people and need to be safe. You may write test systems that deal with hazardous chemicals or radiation. Some of you are working in biomedical fields where that security and stability is critical. Or you might just be testing something that's really expensive or needs to be up 24/7. Or 100 other reasons that I can think of why someone needs to trust your code beyond just you saying what it is. So to start, I want to ask a few questions of our audience. So if everyone can go ahead and find the chat window, if you expand that window on the right side of the screen, you can find that chat. Several of you have already found that and have said hello. I have just a few questions here, and I'd love if you could just type some answers just so we can get a sense of who's joining us today. So the first thing I want to ask is what your role is. Are you a senior LabVIEW developer? Are you a compliance officer? Do you have certifications like a certified LabVIEW architect? If anyone wants to chip in, just post something in chat and let us know kind of what roles you're playing. All right, not seeing it just yet. Hopefully we can get some participation. I'm also curious about the applications that you're working on. Are you building test systems for aerospace parts, or maybe a flight hardware for defense products, or wind tunnel data systems? All right, we got some. Oh, Ravi's here. Hello, Ravi. One of our LabVIEW champions. Fantastic. We're getting some great info in now. I'm also curious about what standards that may have brought you here today. A lot of you have questions about security. Was there a NASA standard or a Department of Defense standard or a security standard that you need to be able to apply to and you need to be able to meet? And then finally, what are some of the goals that you have? Do you just want to make your product more secure? Or do you just need to check that checkbox so that you can meet contractual requirements? Or maybe you want to train your team. If any of you have any questions that you want to be sure to answer, please find the Q&A box. It's a separate box next to chat in the window. I see a few of you have already added a few questions there. That lets us add those questions and we can pin them, and then our team can answer some, or we may answer some in the presentation. All right, well, thank you all for contributing. That gives me a good sense of kind of who's here. Let's jump in. So, as I said, when we did this NASA project, we had to comply with NASA's 7150.2D procedural requirements. This is not only one document, but it's a web of interconnected documents, requirements, and standards that mean that we had to build out an entire software development plan to rigorously say how we're going to develop, validate, test, and secure our code. And this was kind of the first time that I really dove deep into what we call the MITRE CWE Common Weakness Enumerations. This is a fundamental standard that so many of these standards map back to. And I know a lot of you may deal with some of these standards, things like CMMC. I know Steve has to deal with a lot of CMMC stuff with customers. The impending European CRA, which is coming into effect next year, which requires rigorous standards. You may be looking at NIST or STIG based standards that require you to do certain procedures. And there are some interconnected links between these, but the common is all of them point back to CWEs in the end. CWEs are this low-level foundational standard, and so that's what we want to build from, so that we can make sure that LabVIEW can speak this common language. So the CWEs are created by an organization called MITRE. It's a unique federally funded R&D center. Think of it as a R&D company that only works for the US government. They work a lot with things like air traffic control systems, but one of the things they do is publish security recommendations and standards that are used throughout industries, not only in the US government, but increasingly now we're seeing adoption by industrial standards and international groups as well. So the thing that we're going to talk about is the CWE, the Common Weakness Enumerations. Think of this as a big dictionary of all of the computer science vulnerabilities that we build into software. So these are the open doors that we leave in code, or the protections that we may have skipped. CWEs are written to be technology and language agnostic. They're not for C++ or for LabVIEW specifically. They're designed to apply to any technology. And increasingly, as you saw, this is the common language. Because all of these standards are founding on CWEs, it gives us a framework that we can use to approach security systematically and approach proving that we're secure systematically. One quick note, there is often confusion between the CWEs and the CVEs. So CWEs is that dictionary of computer science vulnerabilities in a generic form. CVE are specific exploitations of those CWEs. So a CVE may say, if you're using a specific version of the Apache server, it's vulnerable to command injection. The CWE is command injection, just to differentiate. One of the things MITRE does is publishes an annual top 25 list of the most dangerous software weaknesses on the software landscape today. And as technology changes, they update this list. You can see the little green and red arrows that shows how some of the CWEs moved up or down from the previous year's ranking. But if you look at this list, you'll notice these don't really apply to LabVIEW. If we look at cross-site scripting, that's not something we typically do in LabVIEW. If you look at out-of-bounds write, that has low-level memory management. That's also not something we typically do in LabVIEW. And so at JKI, we found that this list really wasn't a great place to start for LabVIEW developers as far as which CWE should we be concerned about, which should we be addressing, and which should we be documenting. So JKI published our own list. We made our own CWE top 25 and published it as a blog article. You can find this on Google. If you trust my QR code, I'll let you decide if you should do that. Or you can just Google JKI LabVIEW top 25 and you should find this article. Now, who is JKI and why did we decide to do this? So JKI has been a LabVIEW partner for over 25 years. We've worked in nearly every industry that LabVIEW touches, from biomedical to semiconductor to aerospace. We've created a lot of the fundamental tools, things like VI Package Manager, which you may use to install toolkits, or Karaya, which you may use to do unit tests. And recently, we've had a big focus on security. And so we leveraged our team's extensive experience in LabVIEW, touching every different industry, touching our aerospace projects, and said, which one's actually most important to LabVIEW? So we'd like to suggest that the JKI Top 25 can now be another one of these lists or standards that you can cite when you're building out your security plan and say, here's how we're adjusting the JKI Top 25 for LabVIEW. Because we found that MITRE list wasn't quite applicable. The list is published as part of that news article, and I've organized it into a periodic table. just for kind of visualization purposes that lets us see how things are grouped. And I'll actually pull this page up right now. And again, you can find this from the top 25 article. If you scroll down, there's a version of the periodic table, and you can open up the full screen version there. And this just allows us to look at the different categorizations. So this list includes both the MITRE top 25 as well as the JKI. So we can see that MITRE focuses on things like the web server attacks or low-level memory management, whereas the JKI top 25, low-level memory management and web server attacks are not as critical for us. But things like race conditions, infinite loops, and info and logs are much more relevant. You can also look at a list view according to the JKI rank and go through. You'll see MITRE's description as well as our JKI note on kind of why we decided to rank it there or why we decided not to rank it, because there's as we get towards the bottom, there are things that MITRE ranked but we did not. So I would encourage you to play around with this list and to explore it and sit down with your team and ask the questions. You know, how do these affect our software? Some of them may not affect you at all if you're not using specific functionality. Some may be critical. So today I'm going to highlight a few of these so that we can see how this applies to LabVIEW in unique ways. All right, first one we're going to look at CWE 78 OS command injection. So this is an ability for external users to inject code into our application that causes it to do something malicious. So as you can see there from our comic or from our classic XKCD example, there are ways to exploit this in other languages that are very easy and pervasive throughout the entire application. But in LabVIEW, because we're a graphical programming language, it's a lot harder to inject text-based code into that would do something malicious, with one notable exception. Well, I guess a few notable exceptions, but one primary one. So how many of you are familiar with the system exec VI? This is a VI that we use in Windows application that allows us to run Windows commands, just like we would if we were running from the Windows key R command prompt window. And from this interface, we have tremendous amounts of power over our operating system. We've made a small little sub VI here that we want to go in and find a task by name and find its process ID number. So here we can see we have a little format string or task list, and then we want to filter that based on an image name that equals a name that we provide. And we expect that our user is just going to enter in the name of the application, my app.exe, and that everything will be safe. But because we're just adding that string to the end, there's chance for malicious attacks here, where all they have to add is this small command. And does anyone know what that command is going to do? That is going to delete your entire C drive recursively without asking any questions about it, quietly. So obviously in this case, this could cause a lot of problems. So we recommend that if you have system execs, one, you should audit and identify where all the system execs are in your code. And two, you should decide how to protect it. So for instance, we could add, maybe instead of letting you choose any list, we give you a list to choose from, because in our use case, there's only a few valid options. Or maybe we could validate that the process name you gave us is valid by checking it against a static list before injecting it into our command. I actually had a version of this VI, and I rewrote it so that it used the task list, got out the entire dumped task list, and then I used LabVIEW to filter through that list so that I was never actually passing those strings into the command line. So you definitely want to know where in your applications you're calling sysexecs, and be sure you understand how strings from the users could possibly get into that. Our number one CWE is actually input validation. The reason we ranked it number one was because of how pervasive this is in LabVIEW, that you may not be using system execs, or you may only be using a couple, but nearly every LabVIEW application has lots and lots of user terminals, and often completely unprotected. So yeah, if you look at my screenshot there, I want you to see how many malicious or maybe unexpected things that you could spot, whether it's an invalid data rate of -1, a motor position at e to the +25, invalid characters in our channel name. Maybe for your physical DAC channel, you didn't want to support remote systems. but because of DAC-MX, that's just supported by default. So how are we going to protect against these? So here's just a few tips that you may be doing now, but maybe something you need to enforce more consistently. If you have numeric inputs, you can certainly use data entry validation. If you right-click on that numeric and go to the data entry tab, you can, by default, it's just going to use the default limits, but you can instead opt into coercing, which means if you enter a value outside of the range, LabVIEW will actually automatically coerce it to that value. You can choose to ignore bad values, you can choose to coerce them, or you can choose to reject them and reset them. So that allows us to do it in the front panel, and now a user using our user interface can't inject that invalid value. Now you may be reading that number from a file or maybe passing it throughout code, and so it's also good to do in-code validation. For instance, using the in-range and coerce sub-VI, one that I use a ton in my code, to validate that our data rate in this case is between 1 and 10K. And if it's invalid, we'll actually get out a nice, clear user error that tells us exactly what's wrong. So now not only did we make our application more secure, but we've also made it a better user experience for someone who may have entered a value incorrectly, not necessarily someone trying to make a malicious attack. String inputs are certainly the most dangerous because of things like command injection. And so I definitely recommend having robust string validation. And whether that's simple things like using the right-click menu to limit to single line so that you can't have multiple lines, or using regular expression. So I'm a big fan of regex 101, where here I've typed out a few valid channel names and a few invalid channel names. And I've said, in my case, I only want to use letters, numbers, colon, underscore, and dash. And so only character names that use those exact characters are valid, and all others, again, I will receive a nice error that tells me exactly what's going on. I could even add some helpful info to that error message and say, here are the valid characters and invalid characters that you allow. All right, next, we're going to tackle 4 CWEs all at once. And I'm going to go quick on this because Kyle is about to school us on memory safe languages. So as he's presenting, I want you to think about the fact that because LabVIEW is designed to be intrinsically safe in memory management, we don't have to worry about pointer addresses and out of bounds pointers. All 4 of these MITRE CWEs are now checked, with a couple exceptions. There are some hardware drivers that use shared external memory, where maybe the DLL writes into a memory location and then expects LabVIEW to read from that. There's certainly some hazards that you can have there. There's also a really powerful NI LabVIEW memory manager. This is a public open source repo that NI has published on their GitHub. It is incredibly powerful and lets you do all of the pointer things that you don't normally want to do. If you're curious about that and you decide you want to take on all these CWEs yourself, my colleague Sam Cayley from JKI recently presented at the Seattle LabVIEW user group, that's the slug, about using the LabVIEW memory manager, and that's a great presentation. All right, we have 2 more CWEs to talk about. 798, hard-coded credentials. Again, this is one that's particularly easy to do in LabVIEW because sometimes we feel like if it's on a block diagram, it is intrinsically secure, but that may not be the case. Whether it's putting passwords, and yeah, I highlighted the 2 security issues in one, both in that you had a hard-coded password and that your password is password. So in this case, we want to make sure that we don't put private keys or passwords or anything on our block diagram. There are methods that people can use to inspect your block diagram code, even in locked executables, and so that's certainly something we want to be careful about. But it's generally a bad practice. Instead, I would recommend you use credential managers or external files, things like environment files that allow you to read that from a file that you can have much more control and much more visibility and access over. All right, last one I'm going to talk about is one that's in almost every application that I know of, and probably in your code, but is rarely a problem. But every now and then it is a big problem. So common functions like enqueue element or wait on notification have a default -1 timeout, meaning if they don't receive an element into the queue, it will wait forever. It will block and hang your application. I actually had this bite me recently on a large project where there was a queue and there was a subtle race condition that only occurred in this one corner case. But if that happened, the application would completely lock up and we'd have to force kill it to recover. And so we decided, hey, we're not going to put -1 timeouts anymore. I would rather have a long timeout. And in the case of that race condition, the nominal case meant it would always connect in less than a second. And so now I could say, you know what, I'm going to set it to 5 seconds to give me plenty of time. If it doesn't receive an element after 5 seconds, something is wrong. I do not want to wait forever. And so these are all small areas where we can see how the CWEs apply specifically to LabVIEW and how we can take proactive steps to protect our code against those. And how using the CWEs as a systematic framework can allow us to inspect, review, and audit our code in a more systematic and consistent way. So I do want to tell you about tools that we've made at JKI and how we started to meet this. So as I said, when we started on this NASA project, we were required to follow all these processes. We were required to address a list of 38 CWEs that NASA selected for us. They handed us a list and said, how are you going to address these? Now, in other languages, there are static application and security testing tools, things like Black Duck Coverity or Fortify, that will go through and scan your code and identify problematic issues. That didn't really exist for LabVIEW. So JKI made one. We made one at first just for our own internal purposes to use on this NASA project. And over the last 3 years, it's grown into a full-fledged product. So our cybersecurity suite has 2 main components. The first is our software development plan. This is a detailed document that covers LabVIEW-specific development standards. There's a lot about configuration management, about how do you manage your source code versus your unit test versus your user configuration. We have dedicated cybersecurity checklists that cover specific topics like network communication or file I/O. We have guidelines on how to create assurance deliverables, whether that's a unit test evaluation report or a holistic cybersecurity assessment. And the Heritage Qualification Guide helps you apply that retroactively, just in case you're not in a situation of starting a brand new project with a blank VI. We do have a NASA 7150 version that covers a lot more of the NASA-specific requirements. But in this document, we have LabVIEW-specific guidance for 73 different CWEs. And you can see we're also expanding to cover NIST 800 and starting to dip our toe into EU CRA and ISO 9001 standards as well. So the SDP is the first part. The second part is our custom static analysis tool, JCrawler. So JCrawler is a LabVIEW-specific static analysis tool, similar in vein to VI Analyzer, but unlike VI Analyzer, is not only limited to VIs. Crawler can analyze any file in your repo, but specifically run LabVIEW tests on VIs, controls, classes, and LV-libs, as well as things like malleable and template VIs. This allows us to systematically look at every single VI in our repo and, one, make sure it's not broken. Make sure things like we separated compiled code or turned off automatic error handling. But in our latest version of JCrawler, we also have added the capabilities to do security checks so that we too can have this static analysis and security testing. Once you get JCrawler, you can run it manually through LabVIEW, through a PowerShell CLI. A lot of our customers will integrate it into their CI/CD continuous integration, continuous delivery systems in Bitbucket or GitHub or GitLab or Azure, so that now they can have these checks run on every commit. To give you a little more detail, here's what some of the security rules look at. So we have a specific security rule for CWE 78 and verifies that, one, it finds everywhere in your code where you use system exec or where you're calling a DLL, and identifies anywhere where you've passed something other than a string constant into that. And so anywhere where you've called that, we're going to flag that as a warning and say, hey, you should go evaluate this. Now there at the bottom, you can see I added my own custom regular expression validation and said, in this case, this should address it. I don't allow spaces, so now, or ampersands or quotes. And so now that attack we looked at earlier is not possible. I'm also going to limit the max length of my string. So I add this bookmark to show Crawler that this one has been addressed and is okay. We can also identify everywhere in your code where you've hard-coded a -1 or where you've left a default -1 unwired. So once you run your scan on your code, we just released our JCrawler Explorer. this is an application that lets you look through the results of a scan, and I can specifically look at CWE warnings, in this case, a CWE about that deadlock timeout. This allows me to go through my entire code base, and I can even look at the evaluated instances and see the exact bookmark where someone said, this one's okay, and this one doesn't need to be addressed. So if you're interested in trying out these tools, the JKI Security Suite is currently in early access phase 2. We're planning a kind of our major release for NI Connect 2026 in May. So definitely, if you're planning to go to NI Connect, please come find us and learn more about it then. If you want to get on board now and help us shape the final pieces of this product, we'd love to talk to you. You can reach out to me or anyone at the JKI team. Ultimately, we want this to be part of an overall solution. This is the actual pipeline that we use for our NASA StarGoat product, where now we have our development standards, we have our peer review process that's spelled out in the SDP. We're using JCrawler and finding things. We're also using Karaya unit test and our own test integration engine and build automation. So now every time I have a commit, I can get clean, verified artifacts out. All right, there's 2 more quick things I want to tell you about. Over the last year, both NI and JKI have received a lot of questions about SBOMs, about bills of materials, and about understanding exactly what code is used in your application. Now, NI has done a great job from their part of creating SBOMs for the LabVIEW and NI products themselves. JKI is looking to contribute to that by helping you find the code that's used in your application. So many of you may know about VIPM, a way to install and download packages, whether internally or externally. We also have a tool called JKI Dragon that's free and available for any version LabVIEW 2020 or later. When you add it in your LabVIEW project, you get this extra item down there at the bottom that says package dependencies. So now I can see in this is actually Tom McQuellan's MIDI piano application. I can see that he used the JKI state machine, and using the right-click menu, I can go find those callers. I've used this recently to identify packages that I'm barely using, a package that I'm only using in one place in one VI, where I can say, you know what, I'm just going to write that VI myself, and now I can eliminate an entire package from my dependencies and make my application and SBOM simpler. Moving forward, JKI and NI are going to continue our partnership that we've worked on for decades. NI and JKI have partnered to work on package management and distribution, and we're going to continue to work on that on software bill of materials. So please stay tuned. And again, if you're interested, if you have an urgent need for SBOMs or have specific requirements, we'd love to hear from you so that we can be sure that the solution that NI and JKI work on together addresses that. Last little plug I wanted to mention is the JKI Pulse. This is our new newsletter. The top 25 CWE list was actually published in the first version of this, and we have another version coming out next month. There's a version on LinkedIn, and if you just Google JKI Pulse, you can find that. We'll be publishing lots of security tips and articles in that. So please stay tuned. All right, so that's it for the LabVIEW Security Primer. I hope you learned a little bit about CWEs and feel a little more comfortable approaching that systematically. I'll now hand it over to Mr. Steve Summers to take us off. Thank you.